I think we can start. So it's 12 o'clock or 12:01. Welcome to a new edition of AI Lights. Also a very warm welcome to the people who are joining from the Swiss Data and AI Meetup group. Great to see you here as well. So 2 years ago, everyone was racing to build the biggest model possible. And then the question shifted somehow to do we actually need all of that? And so in our today's session, we are making the case for small. I'm very happy to welcome Professor Masha Kubitz-Bricki, who will talk about the potential of small language models in the development of AI agent systems. Masha, it's so great to have you here with us. Hi.
Hello, everyone. Thanks a lot for this nice introduction. I'm very happy to be here. So I'll just share my screen here.
So I will do some more information. I will do some more introduction of you, of course. So Masha Kubitz-Bricki is an AI expert and professor in computer science. She has been working as a professor of data engineering at the Institute for Data Applications and Security, IDAS, at Bern University of Applied Science for 7 years now. And Masha works as well as the co-lead of the Applied Machine Intelligence Research Group and the Generative AI Lab at the Bern University of Applied Science in Biel. Her research focuses on the topic of fairness and the digitalization of social and community challenges. And in 2025, Masha founded Makubri Technologies, where she creates formats that make AI more understandable and engaging. And among a lot of other projects I have seen, Masha published 2 books for children aged 3 to 7 that explain computers and artificial intelligence in a playful way. And the books are available in English, German, and French, maybe in Italian too sometime, and not yet, but soon maybe, and are available in all bookstores across Switzerland. And before we start, let me share some information about the setup, maybe for people who are joining the first time. This session is being streamed live on YouTube and on LinkedIn, if it works this time, and can be accessed later on in our library. And we invite you to drop your questions in the chat, and we will do our best to answer it in the Q&A session afterwards. And today we will have again 10 minutes networking session after the session where the streaming is switched off, and you can present your project, announce events, or connect with others. That's all from my side. I hope you have your lunchbox ready. And now over to you, dear Masha. The stage is yours.
Thank you very much for the nice introduction. I'm very happy to be here to talk about small language models. So as announced, the talk will be in English, but feel free to ask your questions in German or French in the chat. I will then answer in the respective language. Also very happy, looking forward to the networking session after to maybe meet the one or the other of you there as well. So let's dive straight into the topic. So as announced, we are looking at the potential of small language models in the development of agent systems today. So it's quite a complex topic that we will look at in a short time frame. But at the same time, I want to start with laying out the context and giving some definition and explanations so that we are all on the same page, as people with different backgrounds might be here with us today. So that's why, first of all, we are going to dive into the topic of AI agent systems. So we are looking at how we are getting from prompt engineering, from the fact that we are communicating with a large language model, a chatbot, to the matter of context engineering, which is one of the challenges we have when we have a more complex agent system. We then look at small language models, as promised in the title. And in particular, we are looking at advantages and challenges when we can use small language models to improve our AI agent systems. So we will stay at a relatively high level, but the aim of this session is to give you a basic understanding how these things work, how they relate, what are the challenges, and what are the next steps for you, whether you have to decide you want to take it as a strategic topic in your organization, to understand how we can leverage this potential of small language model in the context of AI agents. So let's start with a very short history of AI. So AI, even though it seems that we talk a lot about AI since the release of ChatGPT a couple of years ago, it has a very long history, whereas the first concepts were already in the 40s and 50s that they were developed. And the first chatbot back then, Eliza, was developed in the 60s. Of course, this is very different from the AI we have nowadays. So the systems back then were often rule-based, and as time went on, the more data-driven machine learning approaches were actually put into practice, where at a specific moment in time, the necessary data and compute resources were available. The term AI, so therefore, today mostly refers to applications with machine learning, and in particular nowadays is often used in the context of large language models. Whereas we have to see that from all the things that we can solve with machine learning, this processing and generation of text is only a part of it. However, a very prominent part given the recent advances in the field. In addition to large language models, we, of course, nowadays also often talk about multi-modal models, so models that are including not only text, but also other types of data, as let's say, for example, videos, audio traces, images, and so on. And very recently, so even more recently than the large language models, the topic of AI agents came up to the discussion. And this is what we're going to focus on here today. And this is also where a lot of potential lies for future applications. As most of technological potentials, there are some risks associated to it as well. And the basic understanding of how these technologies works help us to consider these risks when building applications and in that way ensuring that we can make a responsible benefit from the technology. So as said, as of today, when we talk about AI or large language models, here abbreviated as LLM, we often think about chatbot applications. This is maybe now one of the main types on how we interact with this kind of systems. So I don't think that this necessarily always needs to be the case. There are and will, especially in the future, be different applications where we might have different interfaces than a chatbot, but still we can benefit from this kind of modeling. Examples can be, as we see it already now, the correction of texts or suggestions of text while we type in any other application. But let's stay for now with this format of chatbots. We have realized, and I think it's something that is quite broadly known nowadays, that it really matters how we are writing our prompt, so how we are writing the message to these chatbots. If we have a very simple prompt with very few context, then we might get a very generic answer that is maybe not suitable to the problem we are trying to solve. Because when we are talking to an LLM, there is less of general world knowledge, general context, as if we were talking to a person. So if, for example, we talk to somebody in the office, there is a lot of common ground of understanding about processes, about the environment, and many different aspects. With the model, the large language model or a chatbot, we have to be much more explicit. So we see that when we have a complex prompt with more details, where we specify the style, the length, we might get more suitable answers, solving our problem better. So this fact has inspired this term prompt engineering that is used a lot, where we are writing better or more elaborated prompts to get better answers from chatbots. So instead of saying, write a friendly email to move the appointment, we might be saying, write a friendly email to move the appointment with a specific target group, with a specific style, and max 5 sentences to reduce the length. So the more information we give, the better the answer might be. There are a lot of different prompting styles that we're not going into detail here, but just to remind you that with these different styles, for example, a persona, that if we say, for example, you're acting in the role of a software professional, then the system will have some context associated with this profession that we are giving it in the role, and therefore can also give us more elaborated answers. Similarly with chain of thought, where we are asking it to do things step by step. This works quite well, so it does help for this one specific quest. However, there might be some limitations in this approach when it comes to a more general level. So if we want to use the technology to solve more advanced tasks or know more specifically things, then we are getting to a limitation with this system setup where we have a one prompt, one system, and a direct interaction. Because it might be that we need to repeat ourselves, or that we can use a system prompt and integrate our information already there. We also maybe want the system to know better our context in the sense of more than just a more elaborated prompt, but having some structured information that is stored somewhere, some historical data about past operations, and so on. To do this, one way to deal with it is to make systems more complex and to integrate additional data sources. So in addition to our interaction with the large language model with the chatbot, that can have a prompt or a system prompt already specifying some of the preferences, we want to add tools like web search or internal data, like, for example, in the format of retrieval augmented generation. So these are things that have been widely done over the past, that we are retrieving information and combining it with the generation power of the large language model. This requires, to some extent, some collaboration, because it might, for a specific question, not be obvious whether each time we have to fetch data or online information, or whether we just simply need a generated answer. So some decision making started to be there with these kind of applications, as there is more data, as there is more complexity. And this brings us a bit to the idea of AI agent system. Of course, what we see here wouldn't be considered as of today's standard as an AI agent system, but is to show you that we have different components in a system with a user interface. And within there is, to some extent, a decision-making, some reasoning that is there. So if I ask a specific question, there might or might not be the need to search for something on the web or retrieve specific data. And this, with an AI agent system, there can be different components like this that are collaborating together to solve a specific problem the user proposes through this user interface, doing iterations if needed. So here we are seeing this depicted in a slightly different way. Of course, there could be even more arrows between the different boxes, but the idea is to give you here an overview of the different components involved. So in such systems, typically we could have different, now here, large language models, so different AI components that might have different tasks or being sourced, or like being called one by the other, that are interacting with different data sources. Now here simplified could be data sources such as the internet, such as internal data that is prepared in a specific data structure, that are calling tools, so tools in the sense of other deterministic tools like APIs, database queries, and others, and that they have something that we call context, which we will see a bit more in detail, because this is one of the key topics when it comes to AI agents. The context is the information the system needs to be able to elaborate also a more complex request. So if we ask the system to do a series of steps, we need somehow to track these intermediate steps in the process. We need to remember things that might have happened previously in the history. So the most simple example of context is when we are in a direct chatbot conversation, is the context are the past messages, so the messages from the user and the answers that the system has given. Here we have the fact of the context window. So there is a maximum size of information that we can keep track of. So if we have a very long chat history, at some point, we need to aggregate the information from above to somehow condensate it and only keep the most relevant information to still be able to keep it in the current context window so that the model that is answering us, the LLM, can keep track of this information. Otherwise, we might get answers that are contradictory or not suitable to what was said a while ago. So in more complex systems where we have more than just the chat history because we have different components that are interacting together, we need to take particular care of this context. So what typically happens is that we need to sort of memory management. So we need some sort of short-term memory, which is the information that happened just recently. So it's the most typically or often the most relevant information that happened in the past conversation. For example, the task was discussed. We then might need to store other things that happened longer ago. So for example, a previous transactions, let's say if we are in the context of booking a travel, then we might want to store information about the previous travels or preferences of the user. So this can be stored in a different data structure and retrieved as needed, for example, in some form of long-term memory. As mentioned before, with AI agents, we typically have more complex chains of tasks. So we have different subtasks that need to be executed in order to meet the user's goal. To do this, we need some sort of state management to say, these are the 5 steps that we need to do. And we are currently at step 3, and the results from step 1 and 2 are this and that. This needs to be stored and managed. And this is what we see here as the state management. So coming back to what we mean by AI agent systems. A classical large language model typically has a prompt that the user writes that leads to a response. So it's a direct conversation we have here. With an agent system, we have a goal that leads to a multi-step execution. So we have something more complex, a goal that the user wants to achieve, and we have different steps that need to be defined, coordinated, and executed within this AI agent system. So as an example, in a classical prompt, I could be saying, summarize this report and add this additional data source. For an AI agent system, the task or the goal of the user could be research competitors, analyze them, create a strategy, and send it by email. So we have a more complex, different tasks that need to be elaborated by the system. So if we get back to the image we have seen before, meaning that we have different LLM components, as we have seen it here on a quite high level, we have data sources, we have tools, we have context, then of course the question comes up that one of the drawbacks of this kind of situation or this kind of system architecture, even though very efficient, might be the API cost and the compute power. So we need different large and power-hungry components here in order to set up this system. This might also impact the latency. So when we are using API services on these different components, making complex requests to reasoning models, it might take some time to get back and thus produce the user answer. This can be fine depending on the application context, that the user, for example, leaves the system with a goal and then comes back later to get the results. But it really depends on the application context. We also, of course, have the ecological concerns when running a lot of large models to solve a relatively simple tasks, and also the matter of scalability. So whereas many things work quite well as a demonstrator, as a proof of concept, it might be very challenging to maintain them as efficient when having 100,000 or 10,000 users doing these kind of operations in parallel. So here is where the small language models come into play. Small language models, as compared to large language models, are smaller models that have millions to few billions of parameters. So they are smaller than what we have typically today as state-of-the-art models, and often they are more task-specific or optimized. So the models that are provided can be adapted to a specific task to actually work better. So here's a bit similar as with the terminology of AI, a term that is used quite broadly, similar to AI agents, where the term AI agent per se should include some reasoning, but is often used also for systems that are more like a pipeline of different models and fixed defined steps. So similar to that, the term of small language models does not have like a hard definition, like this is a small language and this is a large language model. But just to give you the intuition, typically what we mean is millions to few billions parameter as of today. Might of course be different in the future. So we see that small language models are typically then relevant when we can be more efficient and we are able to narrow down the scope to think about specific tasks. One example here that I found quite interesting, I came across recently and I brought it here to this presentation, is the evaluation. So the evaluation of large or small language models in general typically happens around benchmarks. Now, one such benchmarks is the MMLU, so the Massive Multitask Language Understanding benchmarks, that is often used as a mark of comparison how a model performs across a wide range of subjects. So here we have to see that it's a difficult task. So even for us as humans, we wouldn't typically excel in all of these fields because either we are a legal expert or we are an expert in math, but we are not necessarily experts in all of these domains. However, so given that it covers a wide range of tasks, it's often used as a proxy for general reasoning ability of the model. So to see if a new model that appears is better than the previous ones or not. However, and this is where the challenge of the small language model lies, many tasks do not need general intelligence over all of the fields. We often have tasks, and this is especially the case when it's about agentic systems, that we narrow down the scope, and then we need expertise in this very particular scope and not in all of the subjects. So this means that in the field of small language models, a partial score of the benchmark can be sufficient for some of the tasks. And to give you an intuition on what that means, I have here some numbers that were presented in this source as a comparison to show how fast even small models are getting better. So these numbers are from 2023, and we saw that within only a couple of months, the models reaching 60% on this benchmark, on this MMLU benchmark, were drastically becoming smaller. So within a couple of months, even the Mistral 7 billion parameter model managed to obtain this benchmark. So we have had then and after a very fast development of small models that are getting better. So small models that are giving us the opportunity to solve problems with smaller instead of bigger problems, bigger models that then allow us to benefit from the advantages. So of course, again, here, this is a general purpose benchmark. And if we have very specific tasks, of course, we also need a corresponding evaluation for the specific task, which is itself a tricky topic and maybe more for a separate session. So what we need to learn from this is that we need to reduce the scope. So if we want to benefit from the small language model, we cannot have the expectation that we have a chatbot that answers on all of the questions on all of the topics. if we want to benefit from the small language models, we need to narrow down our task. Now, this is true for general applications with AI, as well as AI agent systems. So the point is that, for example, instead of saying that we want a general purpose code generation assistant that is able to generate code and modify code in all of the languages, and using all sorts of unknown interfaces and APIs, rare edge cases, and so on, we are looking for something that is specialized on one specific programming language in a specific application environment, for example, in software in a given domain. So then we have a much better chance to get our application running with a small instead of a large language model. Similarly, it's much more difficult to capture in a model all of the knowledge about policies in general in different countries under different regulations. Whereas it's easier to use a small language model as a model to discuss questions about specific policies in the company. So maybe if we have an internal system where we want to provide Q&A about specific policies that are relevant for the collaborators of this specific company. So here in this kind of use cases, we have potential to use small language models. Now coming back to the AI agent system, especially with AI agent systems, the different tasks can be very narrow. Because as we saw before, the aim is to have this complex goal and split it down in different tasks that will then be solved by different components and put together to provide or send by email, as we saw in the example before, the aggregated results to the user. So here the question, the strategic or technical question we have to ask ourselves when designing the system architecture is which are the tasks that can actually be replaced by a smaller model so that the overall resource need of our system architecture can be reduced. So if we're coming back to our system overview, we can, for example, have specific tasks that do require this complex general purpose reasoning that large language models provide us. However, there can be other tasks that are simpler, where we don't need this particular capability, and that can be replaced by a simpler solution. So, for example, by a small language model. So let's have a look at an example here. So this is more of a bit of simplified example that looks a bit like a pipeline, but it's just to illustrate how this could look like. So if you have a user request that describes the goal that the user wants to achieve, we often might need some sort of orchestrator. The orchestrator aims to understand the user's goal, breaks it down into tasks, and decides what to delegate and where to delegate and how to solve this problem. So here we might need, in this example here, depends of course on the application, a large language model to handle this complexity. The delegation, however, then often can happen to more specialist system components. Now this can be tools, simple APIs already solving this problem, deterministic scripts that can simply compute what is needed, or cheaper models like small language models or even machine learning classification models. And here in this example, we might then have a lot of information that need again to be aggregated, which can be again a more complex model. It could in other cases be a simple tool that is sending emails instead of a LLM synthesizer. It really depends on the goal of the application and its application context. Here I want to now summarize the potentials and limitations of small language models across a couple of different important dimensions. So one aspect that is relevant is the speed. So the potential of smaller language models is that even if we have, since they're requiring less resources, depending on what we're doing, we might have a faster inference. However, of course, this speed comes at the cost of reasoning. So they cannot one-to-one replace what we can do with a large language model, but they can be a good replacement in those cases where from the needs of the application, it is reasonable and feasible. We saw that given that they have less size, we need less resources. They are cheaper to run and potentially also to fine-tune, if fine-tuning is the way to go for this specific application. However, they might need more continuous training, fine-tuning, or additional sources than a larger model, because they're having less of the general knowledge incorporated in them compared to a large model. The big advantage of small language models is also that it makes it is more accessible to run them locally. In some cases, small models can even be deployed directly on device, with then also a local execution that is good for privacy purposes. On the other side, again, the limited model size restricts the general use cases. So the general knowledge that is inside the system is limited due to the size. So that's why they are good for, this is what we have seen before, for specializing. They can be good at very narrow tasks, at very specific applications, whereas they are not comparable to a general chatbot, such as the AI assistance tools that are now widely used. In terms of efficiency, we have a lower energy and memory footprint, which again comes at a cost which can be in the sense of context size or multi-step reasoning. So what does it mean when we are building such a system? So let's say we are composing this system architecture. So we have a goal, we have a problem that we want users to enter into the system. And now we need to build up this system architecture with the different components. So what we have to ask ourselves for each of these system components is that, can this task be solved with a deterministic tool, for example, a script? And if yes, then we should do so. I'm saying this because I see that often, or that it happens, that people are solving problems with very complex models that might be able to be solved with easier or more deterministic tools. And I think if we have any possibility of doing it with a smaller or a simpler model, then that's the way we should go. In the second step, so if we cannot solve it with a simple tool or deterministic script, then we can ask ourselves the question whether it can be solved maybe with a small language model or even some other machine learning classification model. So we're talking a lot about LLMs, but we shouldn't forget that we can also train other machine learning models that might, in inference, be more reliable and more efficient. That could also be used for some purposes, for example, in terms of classification. We then can also think about the complexity of the task. Does it really need to be that complex and that general, or can we shape it in a way that to narrow it down to be actually solvable with a less big or complex model? And finally, if we really have that important task at hand that is so complex, then we use the LLM because it's definitely the right choice for many, many applications, because state-of-the-art models are really good at some things that can definitely not be solved by small language model or more simpler models. So this brings me, before wrapping it up, to one other very important point. So when we are dealing with these kind of applications, I'm also often referring to the term augmented intelligence instead of artificial intelligence, because I think what we technically have now and what we should aim at is not some sort of human-like intelligence, but rather smart tools that can support humans. And this is still the same with AI agents. It's something I said before for AI in general. So I think that we should be building tools keeping in mind that they should support humans, and also see AI agents as tools, more complex tools that can take some steps autonomously. However, we should keep in mind that the responsibility stays with the human. So the risk management, the considerations of the overall context where this application is deployed, and all of the consequences the application might have needs to be considered by humans, also with AI agents. So as a conclusion, so we see for me, it's not a large language model versus small language models, but more like a plus. We need to build sustainable solutions, which are not necessarily only about the size of the model, but they're also about how smart the overall system is that we build. So it's a lot about system architecture, how different components play together, and how good that is in order to build the best possible system for our given use case. And here, small language model can and will, in the future, make a very important contribution to build efficient and scalable architecture that are actually scalable in practice. So applications that can live beyond the proof of concept, but are actually deployable in the large scale, even for organizations that are maybe not that big or might not have huge data centers. So here I'm concluding this part. Thank you very much. And I'm very happy to answer your questions.
Thanks a lot, Masha. A great overview. And there are several questions in the chat. So you can take a breath and then we can start. So Patrick is asking, for which daily tasks, e.g. in business development and sales, would a small language model be suitable? We have a thought on that.
So business development and sales, I think again it depends on the very specific task. So if we think here, like the first things that would come to my mind is in business development, for example, do some researches, then that becomes harder with a small language model. But in sales, I mean, what we can imagine is that if we have a specific range of products, right? And we want, for example, to provide a tool to answer questions about these specific products. Then I think we have a good chance, as the scope is quite narrow, to provide sufficient information to the model in some sort of, could be fine-tuning or other sort of information retrieval, that the whole system can be sufficiently knowledgeable to answer to give good answers to questions about these specific products. So this could be one example I could think of.
Mm-hmm. And Patrick is also asking, how often or fast do I have to upgrade or switch the small language model given the very fast evolution of AI?
Yeah, that's a bit in line with the question of recommending models. So it's a bit hard in general because this is going so fast. And it's a bit what I can say here. So we mentioned fine-tuning, which can be good to improve the results, but has, of course, the drawback that each time we have a new model, we might need to fine-tune it again. So here, what I think makes a lot of sense to try to combine a small language model that is combined with additional data. So trying this in the first step before fine-tuning it, so that we have an architecture where we have the model that is being decoupled from the data. So if we manage to have it sufficiently performant in this architecture, it means that we can easily replace the model as a new model comes out. So that's very beneficial to design architecture that way. And yeah, how often do we have to upgrade? I mean, here it also depends on what's the benefit we get. So if we have a small language model that is not the most recent one, but it solves our problem, given that we have sufficient additional data we are using with it, we are not such in a hurry to upgrade always to the latest version, as opposed if we are having major issues with the existing setup, then we might more likely want to upgrade more often.
Then we go to Christoph, and Christoph is asking how to make sure there is really a gain of security or data protection by locally hosted small language models if the orchestrating LLM is conventionally integrated as external SaaS.
Yeah, that's very tricky.
Process first.
A very important question, and indeed, it's worth to take sufficient time to look at these things. We are all aware that things are going incredibly fast, but there are concerns, and there is a need to make auditable paths in the system, to have sufficient logging, to actually control the system sufficiently to know which data goes where, and to build in a prevention mechanism on which data should not go to which parts of the system. But indeed, this is one of the big challenges we have with this kind of system that really needs to be carefully examined, especially when we have this kind of hybrid architecture, as it was mentioned here, where parts are running locally and parts are running on some external service.
So next one is from Noreen. I think she is Noreen, female, was wondering if anyone has any women's health small language model contacts. If you had any suggestion for perhaps examples for small language model for health, that would be valuable. Maybe you can help with that as well. Somebody was also answering for the Meditron large language model. I think it's a large one, right? Or is it a small one? Two versions.
There are two versions.
Yeah. Nice. Yeah. Great.
Yeah, I think that's a great question here for everybody in the room. I think indeed this is something that is also needed more specifically. So what we often have is that we have the small versions of the general purpose models, but of course it's very interesting since they are, I said it's good for tasks that have a narrow scope to share openly more different flavors of it. So I think this can be very beneficial in general. So yeah, I think the conversation is going on in the chat, so that's great.
I'm also thinking of Hugging Face. Maybe you can search there by topic, right? For women's small language model, can imagine. Then we have Michi Rechberger. Should I start with the default small language model for easier tasks? And if yes, which one? Or do I need to different specific small language model for every different task?
Yeah, that's a very difficult question to answer, like in general. So my intention here, like my intuition here would be that it's good to try to solve the very specific problem first with a default model, simply because of the fact that it would be easier to replace it with an updated version, right? So I think this is what's meant here by default SLM. So maybe the small flavors of the Mistral or other existing LLMs that can be used. And then in a second step, I would recommend to use this system, but decoupled with the data we have, to maybe try to make the system around it smart enough to benefit from it. And then only then, if that doesn't work sufficiently well, to adapt or develop specific models for specific purposes. So obviously there might be a lot of context where it's needed to create the specific models, but it should only be done when it's really needed.
Okay, thank you. Then Alexandru, how would you rank the costs of paying an AI ML engineer who would be needed for fine-tuning a model versus just using an API of a bigger model without fine-tuning and other additional costs that either path leads to? How would you rank the costs?
Yeah, interesting question. I mean, it's not, I wouldn't say it's only a matter of cost. It's also a bit of a strategic question. So on one side, I mean, again, it depends whether it's an option to run a SLM locally or not. So there might be preferences for running an SLM locally or with a trusted vendor nearby or existing partner that might bring other than just the cost advantage over using third-party LLM. We also need to consider the vendor lock with having a specific API model, so we cannot be sure that the price we have today will be the same in 2 years for these licenses to the really huge models. So this is some sort of risk management where it can be preferable to work with local or small language models, or in general open models. Yeah, other than that, I think it's also a bit of an individual cost calculation. So my suggestion would be to set up the cost calculation for the specific use case, and in addition, consider the strategic and risk management option in order to generate the decision making in such a case.
Okay, thank you. And then we go to, I think the last question for the official part comes from iPhone JJ. So can you compare creating a small language model used trained on that versus implementing a very good context management and prompting system applied, including RAG-eng on a LLM in terms of resources and speed? I would like to get an idea. Wow, guys, you are asking questions here. It's we need to support then Masha after the session with some coffee. Yeah.
Well, I mean, it's a very interesting and relevant question. But again, it's without the exact context of a specific application. It is quite hard to say, but let me try to answer in general. So, so here we have on one side, creating. This is so a bit the two scenarios I have explained. So we have the small language model that we train on specific data, and we have a very good context management and prompting system with RAG on an LLM. For the speed, it depends on a lot of things like the hardware resources and which API we are using, how many users we have, the efficiency of the internal components and the inference and so on. So that's a bit hard to compare in general. But from the resources and performance, I mean, the big thing here are the resource, like LLM. I imagine it infers to third-party tool. So I think we are a bit in the same discussion as we had before for the pricing. So it's also about about having this API costs that might be very high, that might get very high as we scale with more users. That might be unclear about what the price in 2 years might be, because there is a huge consumption of resources, of course, also on the provider side. And and of course, in general, in our domain, it's hard to make predictions over a couple of years, as we have seen in the recent years. But I think it's hard to get more concrete than that based on the quite generic use case. So what I would recommend is really to take one specific example and then either do with external partners a mapping of what are the advantages? So what are the potentials for optimization? And is it worth to optimize this part of the system with a small language model or not? I think it's very individual and based on the application.
Oh, thank you very much. I think we are at 12:48. So thanks again for everyone who was joining today. Thank you, Masha, for this amazing overview and sharing your expertise and answering all these questions. And I will stop now the recording and the live stream, and then we will move over to our networking part. Give me a second. Goodbye. See you next time.
Thank you.